Hi, I'm Matthew Cheung.
And I'm Dylan Riggs.
So, we wanted to use the concept of Markov chains to validate opener strategy in baseball. So, our goals for this was to determine if the opener in baseball is a viable strategy compared to the norm of using a starting pitcher. And to do this, we're going to implement pitching statistics using Markov chains. Doing this, we want to calculate the expected runs allowed for a pitcher and determine how these runs influence their chance of winning a game. To start, we had some definitions to get familiar. An opener is a pitcher that's typically a reliever, and they will pitch one or two innings before the normal starting pitcher enters the game. And Markov chains are mathematical concepts that explain the probability of transitioning between events or transition states in a model. Specifically here, the transition states that we have refer to runner position and outs. So one classic problem in Markov chains is the ant on a cube problem. So basically, we have a cube with labeled vertices, and there's an ant sitting on one of these vertices, and they can move along each of the adjoining edges at equal probability, which would be one third probability. And we want to know how many moves it will take to move to the opposite diagonal vertice. This question specifically, we're asking from vertex 1 to 7. So our cube transition states can be listed as followed. And then the top left would show the transition from vertex 1 to vertex 1. But we are saying the ant has to move, so this probability will be 0. To the right of that, we see the transition from vertex 1 to vertex 2, which is a possible transition and will occur at probability one third. We go along and we fill out our transition matrix, and we get the following matrix with the listed probabilities. And we have to note that each row sums to a probability of 1. This can be represented as a recursive formula, and doing some algebra will allow us to see that the expected number of moves to go from vertex 1 to vertex 7 is 10 moves.
So next, we had to get our data that we would use, and we pulled all of our data from the baseball reference site. First, we looked at data with the 2022 season with Justin Verlander. We used that data just to test our model and make sure everything was running well. And then next, we took data from the 2019 Yankees season, where Chad Green was used as an opener many times. So we thought it would give us the best look at the data for a pitcher that was used as an opener. So we also took data from Chad Green only when he was used as an opener, and then the starting rotation when it wasn't Chad Green, and then the bullpen from the Yankees as well. And then we took the probabilities of all these different outcomes for each at bat, and we used those just based off the stats for those pitchers to get these probabilities. So some more probabilities that we also had to add was when there's a runner on second and there's a single. So we wanted to determine whether or not this runner would score or attempt to score as well. And we used Vijay Asaro's Markov League baseball analysis using Markov chains paper to get these probabilities. And you can see as the number of outs goes up, the probability that the runner attempts to score from second on a single increases. And the probability of being safe from second at home is always the same at 96%. So we had to make many assumptions with our model to calculate these different probabilities. Because baseball is so dynamic, there's a lot of different possibilities that can happen on any play. So in order to simplify our model and make it something that was easier to run and not needing as much data to use, we had to make these assumptions. So the first one is that the runners will move the same amount of bases as the batter, except for a walk, a hit by a pitch, and a runner on second on a single, which we just talked about, because they may attempt to score based on the probabilities that we also just previously mentioned. So, for example, if a runner was on first and a double was hit, in real baseball, you may watch that runner on first score, but in this scenario, we're going to say that they only stay on third. So then, reaching on an error, this will only grant one base to all runners. While if you may see a ball thrown in the outfield or in the stands and it would give more than one base to these runners, we can't be able to see what cases this would have happened at. So we just know that there was an error, so we're just going to grant one base to all the runners. And then when there's double play, we are saying that they can only occur with the force out available. So in this case, it can't be a runner being thrown out at home after a fly ball is caught. And it would only be if there was a runner on first or second and they're out at third or second as well. So to create our model, we had had to define our states of X1 and X2. So X1 is a number and the positions of the runner on base. So in the example here, we have 1, 2, which means there's a runner on first and second. If it was 1, that would mean there's a runner on first. 0 means there's no runners on base. So X2 refers to the number of outs that are currently in the inning. So there'll be 0, 1, 2, or 3. Between all these different combinations, there's 25 unique states for any given batter. So our matrices will be the size of 25 by 25. And then this was a way that we could easily show how we built our model. Each block is 8 by 8. All the white blocks are all probability of 0 because we can't go from those states to one another. And then the other blocks show in either you change the amount of base runners that are on in that case without changing outs, or you change the outs, or there's double play, or the inning ends as well. And then the last row and the last column account for the 3-out state. Then this shows our example transition matrix for Chad Green. And you can see it's kind of hard to read, but there are many different probabilities that can happen and many different ways that he could transition. We also have these for the bullpen and the normal starters, but we're just going to show the matrix with Chad Green this year.
So to attempt to answer our question, we created an opener simulation. So the first scenario we detailed was when an opener starts. Our selected opener was Chad Green during this 2019 season. We said he would pitch 2 innings before the starter came in and pitched 5 innings, and then the bullpen would close the game with 2 innings. For comparison, the second scenario with the normal starter, the starter pitches the same 5 innings, but the bullpen will have to account for 4 innings. So simulation is a realistic scenario of a game which an opener pitches, and this is representative of something the Yankees might have implemented in the 2019 season. So from these scenarios, we were able to calculate the expected runs allowed. And here in both scenarios, you can see what each pitcher would be expected to give up runs-wise. In scenario 1 with the opener, the total runs would be 4.6 runs on average. And for scenario 2, we expect 4.4 runs to be allowed. So in this simulation that we set up, the opener performs slightly worse than the normal starting pitcher by giving up more runs and thus decreasing the chance of winning the game.
So to get these numbers, we had to calculate the expected runs scored. So first, we had to take the original transition matrix, drop the transition states, which are the 3-out states, then invert that matrix. We multiplied that matrix by the identity matrix, which was a 24 by 24, and gave us the expected number of visits to each state. So then we also, after that, we had to create a separate matrix. It was 24 by 4. It showed it was a weighted probabilities of scoring runs from each state. So if you were scoring more runs, the probability would also increase. Then taking the sums of those rows of that matrix, we got a 24 by 1 matrix. And with that, we multiplied it by the inverted matrix that was multiplied by the identity matrix to produce the expected runs for the remainder of an inning.
So some issues we saw with our opener simulation is that the simulation assumes that pitchers always finish their innings and they can only come in with no runners and no outs. This doesn't really make sense as a reliever typically will come in with runners on or with outs in the inning. And since we allotted each starting pitcher to pitch exactly 5 innings, regardless of the scenario, they will allow the same amount of expected runs. So our simulation becomes a comparison between the quality of the opener versus the bullpen. A strong opener that outperforms the bullpen will generally show that the simulation gives them a better chance of winning. But if the bullpen is stronger than the opener, it may suggest that the opener is not as good and won't be a viable option.
So even though this simulation only accounted for the pitchers being in the 0-0 state, our model will be able to calculate out the remainder of the inning so we can actually see all of the 24 active states. It would not include the 3-out state because obviously you would not be pitching in this scenario. So this would actually give us a more realistic view of what could happen in game, where you could plug in a scenario where if you were putting in a pitcher in a state with bases loaded, one out, you could see if that would give you a better chance of winning or losing or giving up less runs with one pitcher compared to another in that state. And this is an example of what we were just talking about, where you can see the expected runs for the remainder of the inning for Chad Green, the starting pitchers, and the Yankees bullpen in each state of the inning. So with Chad Green, you can see with the bases loaded, no outs, he'd be expected to give up 2.156 runs. If it was the Yankees starters with bases loaded, no outs, they'd be expected to give up 2.076 runs. So while it's not much different, it's slightly worse. So it would decrease your chance of winning by a slight amount. The opener strategy can be viable if the opener is of great enough quality in comparison to the starters and the bullpen, is what we decided on based upon this. At best, we can hope that the opener outperforms the rest of the staff, which would lead to a decrease in the expected runs allowed and an increase in the expected winning percentage. So basically, as long as the opener is not detrimental to the team, he can provide crucial innings to a team that may have low depth at the pitching position, be injury plagued, or just looking for a new strategy to use. For example, when using Chad Green in this scenario, the expected difference for runs was only by 0.163. So while it's not many runs, it is slightly worse, but it may be better than what could have happened if you were calling up, say, a minor leaguer for a spot start in that scenario against the top of the lineup for the first few innings.
As far as applications, as it stands, we think this model is good at calculating expected runs for the defined active states by simply inputting your pitcher statistics. We can use this as a tool to compare pitchers on the same staff or roster, as well as comparisons between pitchers of opposing teams, since it uses simply just pitching stats. And we think this allows a team to explore options and optimize their best chance of winning the game by seeing which pitchers will allow the least amount of runs in an inning, given the scenario.
So some future research that we may want to do is we could expand this model to include balls and strikes. And this would allow you to see a lot more different in-game situations. However, this would make much larger transition matrices, as you would have to have each transition state also include the count, which it multiplies the different possibilities by a drastic amount. So it would take a lot longer to calculate this, but it would give you more detail. The next thing that we would look at is how to calculate or how the opener strategy would change a team's in-game ELO rating, similar to a chess, where you can see how the ELO rating changes after each move in a game. So you could look at how, when using an opener, if your ELO rating increases more while using that opener versus using a normal starting pitcher, and see how that changes things. Another thing we would want to look at is the market value of an opener. This high leverage value that the opener has could lead to an increased salary for a player in that role, which we actually saw with Chad Green after the season he was used as an opener. The Yankees did end up paying him more than what he was originally paid the year that he was an opener. And that wraps up all of the findings that we had in studying the Markov chains with baseball.
Thank you.